All right, let's dive right into this explainer and absolutely master the Cambridge International A-Level Nuclear and Quantum Physics syllabus together. Whether you're gearing up for those tough Paper 4 structured questions or, just trying to wrap your head around the bizarre rules of the microscopic universe, you're in the right spot. We're going to stick strictly to the core requirements today, making sure you know exactly what concepts and which cheat code equations you actually need to secure those top marks.
So here's our game plan. We're splitting this into 5 key areas. 1. The power of the nucleus. 2. The rules of decay. 3. Enter the quantum realm. 4. Wave-particle identity crisis. And 5. Atomic energy levels.
Okay, kicking things off with Section 1, the power of the nucleus, focusing on mass and energy equivalence. This is the exact moment classical physics takes a back seat and we see how mass and energy are literally two sides of the exact same coin.
Now, to really understand nuclear power, you first got to grasp this concept of mass defect. I want you to think of mass defect as like the cosmic tax paid to keep the nucleus glued together. If you were to weigh a completely separated nucleus, right, and then weigh the sum of its individual protons and neutrons, the nucleons, you'd actually find a difference. It's crazy, but you lose a tiny bit of mass when they bind together. But in exchange for that lost mass, you get a massive amount of binding energy holding that whole nucleus tight.
And honestly, this just brilliantly illustrates Einstein's famous equivalence between mass and energy, E equals mc squared. The universe takes that missing mass and translates it directly into binding energy. For the exam, you need to know how this principle drives both nuclear fusion, which is joining light nuclei together, and nuclear fission, splitting a heavy nucleus apart. In both of these reactions, a ton of energy is released. And that release? It's entirely dependent on the variation of binding energy per nucleon.
So here's the crucial takeaway. When your exam actually asks you to calculate the energy released in these nuclear reactions, this is the exact cheat code you must use, E equals c squared delta m. That delta m is your mass defect. Just a quick heads up, remember to carefully use the unified atomic mass unit conversions if they give you the masses in U. Do that, and you're going to nail these calculations every single time.
Moving right along to Section 2, the rules of decay, covering randomness and rates. So radioactive decay is entirely random and spontaneous. You literally cannot predict when a specific nucleus is going to pop. And the hard evidence for this randomness is the continuous, jittery fluctuations you see in count rates on a detector.
Now check this out. Notice how the official Cambridge datasheet, the exact one you get in your exam, actually just gives you the mathematical models for this radioactive decay. Look closely at those bottom equations. It's a lifesaver. It proves you don't have to blindly memorize every single formula, but you absolutely must know how to apply them.
You're going to need to calculate the activity of a source, which is just the rate of decay of those nuclei. And even though the decay of one nucleus is random, over a huge number of them, it's statistically predictable. It's modeled by this exponential decay equation, x equals x naught times e to the negative lambda t. Now that lambda in there, that represents the decay constant. It essentially dictates just how aggressively that exponential drop in radioactive nuclei happens over a given time t.
Which brings us to another absolute essential. I need you to keep this specific formula highlighted in your brain. Lambda equals 0.693 divided by the half-life. Connecting the decay constant to the half-life is a guaranteed requirement on Paper 4. I mean it, you will almost certainly be asked to pivot between the half-life of a radioactive isotope and its decay constant to solve an exponential decay problem.
All right, so we've mastered the dense core of the nucleus. We've explored how mass converts to immense energy and how unstable elements just decay over time. And that brings us to our major pivot point for the second half of this explainer. We're shifting our focus from the heavy, tangible foundations of the atom straight into the counterintuitive weirdness of our next act. Seriously, what actually happens when matter interacts with light at the absolute smallest scales?
Welcome to Section 3. Enter the quantum realm, looking at photons and energy. This is where electromagnetic radiation completely shatters our classical expectations and just decides it wants to act like a particle. Instead of thinking of light strictly as, continuous flowing waves, the syllabus demands you understand electromagnetic radiation as having a particulate nature. You've got to view light as discrete little packets, or quanta, of energy. We call these packets photons, and get this, even though a photon has literally zero mass, it still carries momentum. You calculate that with momentum P equals energy E divided by the speed of light c. Oh, and a pro tip here. Get very comfortable using the electron volt, or EV, as your primary unit of energy for this stuff, rather than joules. For this section, this equation right here is your master key.
E equals hf. It locks the energy of a single photon directly to its frequency using Planck's constant. That's the h. It's beautifully simple. If you know the frequency of the light, you know exactly how much energy each of those little discrete packets is carrying.
Moving to Section 4, Wave-Particle Identity Crisis, exploring the duality of nature. Because think about it, if light acts like a particle, but we also know for a fact it acts like a wave, how on earth do we reconcile the two?
Well, when discussing wave-particle duality, the exam isn't just going to ask you for simple definitions, they want hard evidence. As you can see right in the syllabus text, you were required to describe and interpret specific phenomena that prove this dual nature.
You've got to be able to cleanly contrast these two realities on your exam. If a question asks for evidence of wave nature, you point directly to phenomena like interference and diffraction. Like electron diffraction patterns beautifully, indisputably, prove that particles can act like waves. Conversely, if they ask for proof of the particulate nature of electromagnetic radiation, your ultimate trump card is the photoelectric effect.
So what actually is the photoelectric effect? I always like to think of it as a super strict bouncer at a nightclub. A single photon hits a metal surface. Now that photon must have a very specific threshold frequency. Why? Well, because it needs enough energy to pay the work function cover charge of the metal. If it has enough energy, it transfers the whole shebang to a single electron, and that photoelectron gets emitted with whatever kinetic energy is left over.
And this perfectly illustrates the strict rules of our quantum bouncer, summed up by Einstein's photoelectric equation. The photon's energy, hf, equals the work function phi, plus the maximum kinetic energy of the emitted electron. Now listen up, because here is the trap so many students fall into. Increasing the intensity of the light just adds more photons, meaning more electrons are emitted, which increases the current. But only a higher frequency of light increases the emitted electron's maximum kinetic energy. Intensity does absolutely nothing to the maximum kinetic energy. Make sure you memorize that distinction for sure.
Finally, we hit Section 5, Atomic Energy Levels, or as I call it, the quantum staircase. Let's look at isolated atoms and figure out why they only absorb or emit very specific colors of light.
I want you to think of electron energy levels in isolated atoms exactly like a staircase. An electron absolutely cannot stand on the ramp between the steps. It's either solidly on one energy level or it instantly transitions to another. When electrons drop down a step, they release a photon, and that creates an emission line spectrum. But when they jump up a step, they have to absorb a very specific photon, which creates an absorption spectrum. This whole staircase concept perfectly explains why we see distinct colored lines rather than a continuous rainbow when we look at certain gases.
When your exam asks you to calculate the exact frequency or energy of the photon created or consumed during these atomic staircase jumps, this is the final mathematical cheat code you're gonna need. HF equals E1 minus E2. The energy of the photon is simply the difference between those two discrete energy levels. It's that straightforward.
So we've covered the immense power of the nucleus and the strict, quantized rules of light and atoms. But I'll leave you with this provocative thought to truly test your understanding of wave-particle duality before you go. Remember the de Broglie wavelength? Lambda equals Planck's constant divided by momentum. This mathematically proves that moving particles act like waves. So, if you are a moving mass with momentum, what is your wavelength? Think about it. Keep practicing those equations, stay focused on the key concepts, and best of luck on your exams.